We're moving on to the second talk, which will be given by Andreas Jakl and his colleagues. And the title of the paper is Augmented Reality for Industry 4.0, Architecture and User Experience.
Okay, welcome to our session about our short paper, which is called Augmented Reality for Industry 4.0, Architecture and User Experience. I'm Andreas, also Lucas will be presenting the paper, and Markus and Matthias, who are also co-authors, are here as well. So in the previous session, we've heard a lot about potential use cases for augmented reality. If you take a look at this from the commercial side, so where is the money? Many studies show that one of the biggest potentials are in engineering. So this is a study of Goldman & Sachs for 2025, how much billion dollars are estimated to be made by those various sectors, and engineering is one of the largest from the commercial side. So it's of course a good idea to spend some time taking a look at augmented reality for industrial scenarios. Well, literature and also the current prototypes show that most of the use cases currently focus first on monitoring, which means that you get dashboards, that you get status overview of the machines that you have, for example. And the other really big use case with a lot of potential and potential market revenue is remote assistance, where an on-site worker who is maybe not so skilled gets support by a remote worker who knows exactly what to do. And also already early studies, for example, from Boeing, which is one of the most traditional studies in this field, already 25 years old, they already showed how much more effective people are if they have the exact instructions on what to do right next to where they're doing it. So it's a lot better than reading a manual and then trying to repair something if you really see what you're doing, exactly where you're doing it. However, we have seen that there are a lot of challenges. So, I mean, if there's so much potential, why doesn't it work yet everywhere? And the reason is, of course, that the software is a bit different to traditional industry software. We have identified three main challenges for the software architecture specifically. The first one is the efficient data transmission. Because usually, of course, in the industrial sectors, most of the things are wired. And now you suddenly have to work with wireless headsets, with Wi-Fi networks, with phones, which have got limited capabilities of data transfer and also, of course, of processing data. The second main challenge is that you really need to work with devices which are certified for industrial use. So, for example, that have helmets and that can fall down, which is not the case for most currently available headsets. And the third main challenge is that you really need to make the usability targeted towards industrial users. So often it's very loud in factories. I said you need to wear helmets, you have gloves maybe, so you can't use a traditional smartphone in all the scenarios. So to find solutions and to find real answers to those questions, we decided, well, the best way to do it is to try it out and to develop two prototypes to validate our claims and also what we assume would be a better way to do it. And for this, we have developed two prototypes. One is targeting the Microsoft HoloLens for augmented reality, which is real-time mesh and data overlay. And the second one is for mobile devices. In this case, it's Google AR Core for web-based AR remote support. So let's start with the first one, real-time mesh and data overlay. What is it for? Imagine you are the shift manager. You're just taking over the shift from your previous colleague. You just want to walk through the factory floor. You want to see the status of the machines, which machine is working, which is maybe broken, which has maybe issues, potential issues, which could require your attention in your shift. And you just want to walk through it and you want to see what's happening. Well, of course, you can have a huge dashboard in your office, but then you lack the context. And a good way is to really put dashboards right where the data is. For example, if you've got this heating pipe or cooling pipe in this case, you might want to see right there what is the temperature currently flowing in this pipe. And for this use case, we have integrated real machine protocols to show it. I just want to highlight one challenge now, which is in the usability area. So Microsoft, for example, recommends that you place those dashboards 2 meters away from you for the focusing of your eyes, because it doesn't work so well if it's too far away. And then you have got the additional limitation of the resolution of the HoloLens, which is, for example, 720p. So most augmented reality headsets are not so capable yet. And if you then think about that the dashboard is not facing towards you, but it's really like on the wall, you see it from the side, the resolution is too low to see it if it's farther away from you. So this is why we propose and also validated with this that it's better to have billboards which always look at you and which also have deactivated environmental occlusion, so that it's not somehow inside of the object and you can't read it anymore, because the information is after all what you're looking for. For the second use case, Lucas will present it, and we have got a live demo as well.
Thank you, Andreas. Yeah, I was especially involved in the implementation of the second use case. It is web-based AR remote support. Why web-based? We discovered 3 challenges. The first challenge is, as we heard already, the usability should be good. So whenever you need remote support, you need, in the most time, you need it very quick. So there is no time to configure anything, to install anything. So we decided, okay, we need something where the supporting person doesn't need to install anything, and the one who requests the support can really have the support really quickly on his smartphone. So we developed a smartphone application. I will show it now live. You can see what is happening. I'll put my microphone down. So what's happening is I'm now sending an email. So as soon as I start this application, I'm sending an email to the email address of the person who will support me. And now the email should be received. Yes. The next thing what starts now is a live video stream. It is now should be directly streamed to the supporter's browser now. Now I will hold my phone on some interesting point, and Markus will try to make some annotations. Yeah, so Markus is now drawing something. And normally when he says Zeichnen beenden, so stop drawing, it should be anchored at the point where he did the drawing. And now I can freely move my smartphone, and normally, yeah, it should be anchored here. As you see, we have some issues with the exact positioning, because this is still a 2D and not really 3D spatial mapping, but it works pretty well. I can even put my smartphone down, and normally, yeah, it should reappear here. Yeah, that's it.
Okay. So for the software architecture, right now it's 2 separate applications, and to really focus on those specific issues that we have highlighted at the beginning. So the first one is that we identified that you should have a server in the background, because there's a study from Dürenkop which shows the overhead of those machine protocols. I mean, they were not really designed for wireless networks. OPC UR, for example, was the most efficient one, but it's still a lot of overhead if you need to transmit it to the HoloLens all the time. So this is why we think it's better to use a relay server, which really, makes sure that the data is minimum possible that you need. And additionally, it also helps for security, because you don't need to expose your real machine live data to a Wi-Fi network. Second challenge is, of course, the headsets, which need to be specific. So this is why it's good to have two different applications. So for example, the HoloLens, it is certified for industrial solutions. So you can have wear it with a helmet. It has several certificates, but it's okay. And also for the phone side, to be outside, there are a lot of rugged Android devices which you can really use in industrial scenarios. For the persistence, both of those systems right now handle the persistence locally. So if you store something, if you place a dashboard somewhere on your machine, or for example right now on this desk, right now the frameworks from Microsoft and from Google and also from Apple store the information mostly locally. So this was a good basis, and then we thought about what could be improved, and we came up with a unified architecture which actually brings this to the next level. For this, we proposed that there are three main changes to our current architecture, which would then work even better than it did right now for those specific use cases. First one is that we should still use a centralized server, but make it common for both scenarios, because we think actually that both use cases are relevant to be used at the same time. And if you have a central server, because they are kind of similar anyway already, it would save a lot of time and space and work and make it more ubiquitous. Also, persistence should then be managed by the server centrally, which is slowly getting possible by the latest versions of the frameworks of Google and Microsoft and also of Apple. So this will be something to integrate in the next version. For the devices, if you have as much as possible on the server and only very thin clients, it's of course easier to choose the appropriate device for each use case. So if you want to use a HoloLens, or if you want to use a headset, another headset or something else, you can always choose the right thing. Because especially thinking about the usability, if you only have the interaction handling in the specific client, it's really easy to port and to get the exact information need out of the server just for the use case you want. And then you can easily make one client to be used with gloves, one for the HoloLens, and one for other systems. So these would be our main recommendations for unified architecture. And if you like, you can also try the live demo afterwards as well. We decided not to show the HoloLens because of time constraints, but this is working as well. So thank you.
Yeah, thanks for the presentation and for the live demo. I think we have time for 2 or 3 questions. Okay, that's nice.
Thanks for the interesting presentation. You do have 2 prototypes. You do have outlined an architecture to integrate these. So are there any further plans with your work? Or this is a short paper. It was a preliminary state. So what are the future plans with this?
Yeah, good question. So what are the future plans for this one? So of course, these have been 2 small funded research projects, which we kind of found are rather similar. This is why we actually figured out that it would be good to have both in one application. And right now we are starting a lot bigger research projects at our university, where we build upon this knowledge to really make this work as we imagine it should be the best use case. So we already validated several of those claims in the individual prototypes, but this will then go to the next level.
Yeah.
I was wondering, because you made like a very simple drawing, what can you actually do with the content? And is it just like for the prototype that you just want to design anything, or did you use something that already exists? Or, I mean, because I see there are lots of possibilities, of course.
Okay, the mic is coming.
Yeah, as you can see here, we have one real use case here. So whenever someone requests remote support, you can do these annotations, and the user who needs the support can immediately see very which ventile he has to move it first and which is second. So these are the possibilities. We have integrated simple drawing tools like circles, rectangles. Of course, we could also integrate much more things. We could even integrate panels which show automatic values. But for this prototype, we decided to go with very simple drawing tools. But this, as you can see here, can already help a lot. I hope this answers your question. Okay.
Okay. Any more question? Oh, whoa. You go last.
Nice presentation. I just would like to ask if you think the application in this scenario of Industry 4.0, it would benefit for some sensory augmentation, like auditory augmentation, or maybe tactile augmentation, like not only the visual feedback.
Yes, the question if the application scenarios would benefit from other kind of feedback like audio and haptic feedback. So I think definitely yes. So this is why we also think this unified architecture would be a good approach, because then you can use the unique aspects of each of those devices. So I mean, as mentioned, if you wear gloves, for example, then haptics wouldn't work, or if you allowed industry hall, audio wouldn't work. But in some scenarios, maybe you can only use audio because you can't use your hands to hold a phone, or you're not allowed to use a helmet. So it's really up to the scenario which means of communication you would like to use. But augmented reality is kind of everywhere. Further comments?
May I just add something to this question, because right now we are starting one of these research projects that he was talking about earlier, where we have two use cases that are industry related, and one of them is exactly for auditory augmenting of a real environment with virtual audio stuff. Yeah, Michaela is the leader of this work package, and it's going to start next year. Yeah.
Okay, one final, again, brief, please, question.
I'm wondering whether you have looked at the companies that are already in the Industry 4.0 area providing AR solutions for industry. So there's a lot of companies out there like Tsumoko or other ones. And what are they doing, and what is different to that what you are doing?
Yes, definitely. I mean, of course, it's big industry potential. So of course, also the big companies are focusing on this one. For example, Vuforia has got a commercial solution already out for remote support. What we think is the reason why we did it, because it's working without an app. So you can do it right in the browser, for example. You don't need to install something. On the supporter's device, we wanted to make it as open as possible using web standards. Most of the solutions that are existing so far are proprietary solutions which only work with specific apps. And we don't think this is the future, because if you just want to give quickly support to someone, you shouldn't need to install like a 200 megabyte app on your PC. So it's always better if it works in the web. Also for the HoloLens, of course, there are solutions for remote support and for dashboard displays. But again, most of it is currently really proprietary, and there hasn't been much in the open segment so that researchers can actually learn from it. For example, there's an MQTT or OPC-UR implementation, which is theoretically working for the HoloLens, but there are no guides on how to use it. It's really complicated, and we try to actually help others as well to make it possible to make those solutions and bring the research further and not leave it completely in the hands of the industry alone. You want to add something?
Okay, thanks once again, guys. And we're moving to the third and last presentation for this session. This time it's not about augmented reality, but it's about visualization. Talk is given by Robert Goff, and very nice title, It Pays to Be Lazy, Reusing Force Approximations to Compute Better Graph Layouts Faster. Thank you.
Great. Okay. Am I on? Okay, great. Yeah, so I originally had a different title for this talk. I didn't really feel like that was very descriptive, but it did really express my surprise at some of the results I got from this research. So my talk is about some modifications I developed for graph layout algorithms that make them faster by making them less accurate. And the really surprising part is that sometimes this actually gives us better graph layouts in the end. This of course, has some impact on people, data analysts, who are analyzing different kinds of data, like social network data, for example. But these methods I'm proposing can also be applied to other types of algorithms, certain types of dimensionality reductions algorithms like t-SNE, as well as physics simulations. So when we talk about graph layout algorithms, a really common family of layout algorithms are the force-directed layout algorithms, and in particular, the spring electric layout algorithms. So if you've ever used something like D3, this is the kind of algorithm that it's using under the hood. And what we're doing is we're taking a graph as an input, and our goal is to create some sort of general purpose graph layout that allows us to understand the structure of the vertices in the graph, or how people are connected, or how computers are connected, for example. And the way this algorithm works is it models the graph as a physics simulation. So it models the vertices as charged particles, and then it models the edges as springs. So the charged particles repel each other. The springs will pull or push the vertices into certain positions, depending on whether the vertices are too close or too far apart. So this is iterative. So what happens is you compute the forces based on the current vertex positions. You then update the vertex positions based on those forces, and then you go back and you do that over again and over again and over again, and that's what we're seeing in this animation. And it works pretty well. We do get to see a general structure. We get to see what are the clusters of vertices that are connected, and how are the different clusters connected. But the problem is that this is kind of slow. In particular, this repulsive force calculation runs in quadratic time, big O of n squared. And that's because you have to compute pairwise forces between each pair of vertices. So there are quite a few different algorithms we can use to speed this up. I think of these as a family of algorithms: the Barnes-Hut approximation, the fast multipole method, the well-separated pair decomposition. And what they're doing is they're computing a spatial tree of the vertex positions, and then basically doing some math to group together faraway vertices into a cluster, into a single meta-vertex, and then using that to compute approximate forces. So this ends up bringing the total running time down to big O of n log n. And it's a two-step process, basically. First, you have an n log n step to compute this tree, and then you can use that approximation, that tree, to then actually compute the forces. And so again, this is iterative. So we start off based on the current vertex positions. We compute a spatial tree. We then use that tree to compute approximate forces. We use those forces to update the vertex positions. We use those new vertex positions to compute a new tree with new approximate forces, and so on and so forth. And this iterates and iterates and iterates, and we keep recalculating trees. But as you notice, there's not a whole lot of change in vertex positions from one iteration to the next. So my question is, can we just reuse the previously generated tree? Will that work? Will it work well enough? How much performance, runtime performance improvement will this give us? And not just runtime performance improvement, but will this actually give us a reasonable graph layout in the end? So as I've talked about, the sort of standard schedule, as I call it, the standard schedule that these algorithms use is to compute a new spatial approximation, a new tree, after every iteration. Some other researchers proposed updating this tree on a logarithmic schedule. So during the beginning of the simulation, you recalculate the tree very often, and as the simulation goes on, you recalculate the tree less often. However, they didn't really evaluate this. They didn't very rigorously compare their logarithmic schedule to the standard schedule. So we don't really know, we don't really have a good idea of the kind of runtime performance improvement we see, as well as what the impact is on the layout quality. And so this is something I wanted to evaluate. But there are also other different ways that we can approach this. So for example, we could have a uniform schedule where instead of having a logarithmic formula here, instead maybe we just calculate a new quad tree every 10 iterations or every 15 iterations. And in between then, we just reuse the quad tree that we calculated last time. So in my work here in the research I'm presenting, I have parameterize the uniform schedule and a logarithmic schedule, so they both compute the same number of quad trees. So the amount of work here is kind of comparable and allows us to compare the results between them. Alternatively, we could have a dynamic schedule. And so what I'm proposing here is we just keep track of the total amount of vertices, the total amount of movement in the vertices over time, and then once this exceeds a threshold, we calculate a new quad tree. We say that the vertex positions have moved enough that the old tree is out of date, and we need to calculate a new one. And then we reset that sum and keep going. In practice, this updates on a frequency that's similar to the logarithmic schedule, but it allows a little more flexibility. So if vertex positions stop moving early, we'll do less work overall. So to evaluate this, I conducted a few experiments here. I downloaded 50 graphs from a couple of open repositories online. Some of these are social networks, some of these are meshes, some of these are artificially generated networks, so a wide variety of different types of graphs. And what I want to compare here is I want to compare the differences between that standard schedule and these three alternative schedules, the logarithmic, uniform, and dynamic schedules. And I'm doing this in two different approximation algorithms, the Barnes-Hut approximation and the fast multipole method, to see if there's any if the results we see kind of extend beyond a particular forced approximation algorithm, or if they generalize fairly well. And we want to analyze the result of a few different types of results here. We want to analyze the runtime performance, what impact does this have on the runtime performance, but then also quality. Do the graph layouts that we actually end up getting, do they look good? Are they good enough? Or is there some trade-off in quality? So I'm doing this analysis using estimation method. It's analogous to doing hypothesis testing, but we get to analyze the results visually. So I have sort of an example up here on the right. So what we're looking at is if the differences between the alternative schedule and the standard schedule. And we get to see a confidence interval in this horizontal bar, and the circle indicates sort of the average difference in performance between them. So if this horizontal bar crosses 0, we say that there's no statistical difference between the alternative schedule and the standard schedule. If it doesn't cross 0, if it's to the right of 0, then we say that the standard method has a lower value. Yes, the standard method has a lower value than the alternative schedule. And if it's to the left, then we say that the standard schedule has a higher value than the alternative schedule. So onto the results. Oh, maybe one more. Yeah, onto the results. So with respect to runtime, all of the alternative schedules, regardless of the forced approximation method, they have a lower runtime than the standard schedule. So this is good. And we would really expect this. We're doing less work overall, so we do get some performance improvement. The dynamic schedule has a less runtime overall, and then next is the uniform, and next the logarithmic schedule. For layout quality, the first metric that I'm going to show you here is the number of edge crossings. So all of these metrics I'm going to show you, they've been normalized to be between 0 and 1, where 0 is bad and 1 is perfect. And ideally, a graph layout is going to have very few edge crossings. It helps us understand the structure in the graph. And what's interesting here is that with edge crossings, for all approximation methods and all alternative schedules, they all perform better than the standard schedule. And this is what's really surprising, is that we're making this algorithm less accurate, but somehow we're actually getting a slightly better layout in the end. Now, I'd like to point out that these effect sizes are kind of small. The differences in performance are kind of small. They're statistically significant, but it's kind of an open question about whether or not you and I would actually see the difference between the two layouts. The second metric that I looked at was the crossing angle. So when edges do cross, we would like them to cross close to about 70 degrees. We believe that to be the ideal angle that they cross. That allows us to more easily see how many edges there are and what and whether or not they're crossing. And this takeaway is a little more nuanced. The dynamic schedule, for example, always performs worse, regardless of approximation method, or always performs worse than the standard schedule. But the uniform schedule, both for both approximation methods, has no statistical difference from the standard method. So if we were to choose one, we would choose the uniform schedule. The angular resolution minimum metric looks at for edges that are incident on a vertex, what's the smallest angle of all of those? And if the smallest one is really small, that's a big penalty. We would like all of them to be pretty uniformly distributed, like that good layout we see on the right. And so in this case, for the Barnes-Hut schedule, a Barnes-Hut approximation, the logarithmic and uniform schedules both perform better than the standard. In the other cases, there's not really any difference between the alternative schedules and the standard schedule. So again, it's looking like the uniform schedule is performing better so far. And finally, there can sometimes be some issues with the angular resolution minimum metric. It can unfairly penalize if there's one small angle, but otherwise the layout is pretty good. It can unfairly penalize that layout. And so there's other researchers that proposed an alternative metric, the angular resolution deviation metric, which instead looks at sort of the average deviation for all of these angles of all incident edges. What's been proposed previously could sometimes generate a negative value. So in the paper, I have a formula and a proof for a new formulation of this metric that gives you a value guaranteed between 0 and 1, and that's what I used here. And again, we see similar results as we saw with the angular resolution minimum. So the uniform and the logarithmic schedules perform a little bit better than the standard. Otherwise, the alternative schedules are about the same as the standard. So if we were to summarize all of this, if you're using the Barnes-Hut approximation, overall, the uniform schedule performs the best overall. If you're using the fast multipole method, it's a toss-up between the logarithmic and the uniform schedule. You could probably use either one and get similar results. Another important thing to look at is convergence. So not just are we getting good results in the end, but since we're making these algorithms less accurate, since we're doing less work, do they converge slower? And I'm looking at the results of 3 different graphs here, and it turns out that it sort of depends. In some cases, the standard schedule will converge to a slightly better value. In some cases, they all converge to be about the same. In other cases, the alternative schedules converge to a lower value, so that's a good thing. And typically the convergence rate is about the same, but when the standard schedule becomes better, it usually not just converges at the same rate, but ends up converging to a lower value. So that convergence rate is really sort of the main takeaway, is that we're not really losing a whole lot by using these alternative schedules. And here's the audience involvement part. So you might say, oh, well, these are doing less work, and we did these quality metrics, but can we actually tell the differences here? And so here I have these 3 graphs. These layouts were calculated using the Barnes-Hut approximation for all 4 of these schedules: the standard, the uniform, the logarithmic, and the dynamic. And what do you think? You can probably tell that some of them are a little bit different, but can you really tell that one is better than another? Can you see some structure in one that you couldn't see in another visualization with a different schedule? And at least speaking for myself, I don't, again, I can see that some of them are a little bit different, but I can't really tell you that one is better than another. And if you're curious, this is what they correspond to. So to conclude, I introduced a couple new schedules that we can use for deciding when to update these approximation methods. The uniform schedule, overall, I found it not just to be fast, but also produce good quality layouts in the end. The dynamic schedule is a little bit faster. If you really want speed, you could go for that one instead, but you sometimes may have a small trade-off in layout quality. These new schedules I'm proposing, you could apply these to other force-based algorithms, like what's used in the SNE algorithm, for example. You could speed up that Barnes-Hut implementation that's available open source. In the paper, I also have a new formula for calculating the angular resolution deviation metric to give you a value between 0 and 1. And for things that you and the audience can use, if you're doing graph analysis in your own work, I have an open source implementation of the uniform schedule as a plugin for D3. It's up on GitHub, along with the library that I used for calculating these readability metrics. Furthermore, all of the data, all of the code to reproduce these figures and these experiments is all available open access. And if you're interested in just sort of a brief overview of the research, I have a blog post available that you can share with other people. Thank you very much.
Thank you. Are there any questions? Yeah. Let me start in the back.
Did you look at the quality metrics, if they are different for different type of graphs? For example, real social networks graphs versus generated graphs, or different densities of graphs?
No, I didn't. I think that's something that's very interesting to look at, and I suspect that probably there are some types of graphs where the standard schedule would perform a little bit better. But I don't have really good answer to your question, so I haven't really looked at that in detail.
So first of all, thank you also for making all the things openly available. It's a really nice service. I have a question regarding possible reasons. So you said, I mean, even though you have less steps, you even have better results than with the original algorithm. Are there any possible reasons that you would suggest that make this happen?
Yeah, I don't know for sure, but my guess is we're introducing a little more randomness, a little more making the force calculations less smooth. So if we look at this convergence chart, we see there's more bouncing around. I suspect what's happening is that while the standard schedule might get stuck in a local minima, we're introducing a little more stochasticity using these alternative schedules, and it's more likely to jump out of that local minima and converge better to a better value overall. Sort of how you might introduce randomness into a genetic algorithm or simulated annealing. That's my guess. I don't have a proof, but that's my guess.
Okay. Any more question? One more. Okay.
Did you also try with much bigger graphs? Because I think less than 1,000 vertices is quite small, right?
So I did not calculate the readability metrics on this, but in the paper I describe in a little more detail some runtime experiments that I did for larger graphs. So I generated some random graphs with 10 to 100,000 vertices, and then what we're looking at here is the runtime improvement. So this is the percent decrease in runtime. So higher numbers are better, in other words. And for the fast multipole method, which we see on the right, it's kind of even. It doesn't really matter how big the graph is. You typically get a runtime improvement of about 90%. I don't know why for the Barnes hut we see this decrease and then increase for the graph size, but nonetheless, like even in the worst case, you're getting a runtime of improvement of more than 10%, which for such a simple algorithm, I think it's worth implementing and using anyway. And you might end up with a much bigger performance increase.
Okay, so thanks again for the talk. And now is again a coffee break. So outside there's coffee and cold drinks, and we're continuing with the last session for today, 3:15. And the last session will be about human-computer interaction. Thank you.